Next idea is complex logarithmic function. Log of any complex number is defined as natural log of the modulus of z plus I times the argument of z. Okay, so can you tell me why I have written on the left hand side the logarithm in the form of log and on the right hand side it is a natural log in the form of ln? What is the reason? This is the complex log of a complex number z and I have written in the form of log, and whenever I write ln it means I am taking the logarithm of some sort of real number, because the modulus of z is a real number and I can define its natural log in whatever the sense I do. Plus I times, what is this? This is argument of z. Okay, so the problem is this argument is not uniquely defined. We know very well, because this argument is some sort of period, let's say 2n pi, so we cannot define it uniquely. So we have basically so many values for this logarithmic function. We call it a multivalued function, because when you put z and we are getting its argument, we will be taking some sort of multiple values. That's why it is not uniquely defined. So that's the problem with this one. If I want to write this explicitly, if my number is z, which is x plus iy, then I can say that the same thing is log mod of z is square root of plus this argument is tan inverse y by x. But I know very well I can add something into this one, but I will say 2n pi. So for each n I will be getting a different value for log z. That's the problem. And we want it to be defined uniquely. Then we will find out the principal value of logarithmic function. It is something that we are going to do now. And we have some usual properties for logarithmic function, you know very well. Log of the product of two numbers is the log of first number plus the log of second number, and so on. So I am not going in that idea, but we are going to find out the principal value of log z. But can you tell me how can I solve this equation? Let's say it means I have to find some w in the set of complex numbers to satisfy this condition. And how can I find out those w's? You know very well I can write this thing in this form. Am I right? If you take log on both sides and you are done. Now you have to find out logarithm of -2. That's all. And how can you find that out? By applying this particular formula. So how can I find that thing out? Log of absolute value of z. What is the absolute value of this one? It's going to be 2. So I can write -2 because then I will take absolute value, that will be 2. Plus I times argument of z, but I will always add 2n pi. What is the argument of this number? I am directly writing our argument. Argument would be pi 0. Argument would be pi. set of integers. So if I am going to find out logarithm of minus 2 pi of these set of values, which is not a unique value, you can see. So what we call this a multivalued function. When you find out the logarithm of a number. In complex analysis, this happens mostly. And what about this thing? Like when you find this square root, how many answers do you get? 2 answers. But basically, this is only 1. The answer is 2. But when you say, okay, how many solutions to this equation are there, then you can say this thing. But if there is no any sign plus minus here, the answer is always 2. There is only one answer, not 2 answers, only one answer. But when you treat this number to be in the set of complex numbers, then square root of 4 will be 2 answers. Like in the set of complex numbers, square root of 4 will take 2 answers. In the set of real numbers, it will take only one answer. This is the thing that we should keep in our mind. Otherwise, if you solve this equation, you have 2 answers, plus and minus 2. So what is the principal value of log z that makes a logarithmic function to be getting a unique answer, so that we can find out the inverse of that function easily. So if a function is multivalued, you cannot find out its inverse. You know very well. For example, I have a function, let's say y square is equal to x. It's basically not a function because its graph looks like this. If you take any fixed x, then you get exactly 2 answers. One is, let's say, y1, another is y2. So it's not a function. It's not a function. But it is a function. It is a function whose graph looks like this. But this function is not 1. Is it 1? No. Not 1. Okay. So because of there is an horizontal line test, cuts at 2 points. So we can say that this function is not bijective. So there exists no inverse for this function. Okay, the inverse of this function does not exist. So similar is the case in complex analysis. So I am going to continue this thing and let us see what is the difference. So principal value of log z. It is denoted with capital log z, the first thing. The generalized value is small l, and the principal value of log z is denoted by capital L. So it is same as this because it's a real number, log z plus I times, now this argument becomes this principal argument. And you know very well that the principal argument lies between minus pi and plus pi. So that's the difference. We'll be doing these things maybe in detail later on when we are going to do some similar topics. But right now we'll be doing something what we call the complex differentiability. That's a bit important. So the definition for limit, the continuity, the differentiability in the real and complex system. The definition. The same epsilon delta definitions will be used for continuity, for limits and so on. But we will be dealing with what we call the CR equations, because in real analysis or in the case of real valued functions, what do we mean by a continuous function? Continuous means the function's limit must exist, left and right hand limits must agree, and the value of the function at that point and the limit must be same. This is the continuity. And what is differentiability? Differentiability means there is a particular limit. If it exists, we say that the function is differentiable, otherwise not. But it is the differentiability once. It is differentiability once. What about, okay, whether this function is differentiable twice or not? Whether this function is differentiable thrice or not? So this is very difficult in the case of real valued functions. But in complex valued functions, if a function is analytic, it means it is continuous, it's differentiable once, twice, thrice, and so on. So once when you are guaranteed with analyticity of the function, you can say that the function is differentiable and its derivative is also differentiable. If the derivative is differentiable, means the function is twice differentiable. And if the second derivative is differentiable, it means the function is thrice differentiable. So this goes on forever. But this is not the case in the case of real valued functions. Can you tell me a function which is continuous but not differentiable? In R, mod x. In R, if you take this function, so we say that it belongs to, let's say, C of R. What do you mean by C of R? A set of continuous functions on R. And sometimes we restrict our domain to D. The set of continuous functions in some closed interval. We call this a compact set, and this R is not a compact set, you know very well. But we are not about to discuss these all things. This particular function belongs to this one, but I think it does not belong to. What do you mean by C1?
First derivative.
Differentiable ones. One derivative. So it is continuous, but it is not differentiable at 0 exactly. 0 is part of R. That's why I have written whole R. Can you tell me a function which is differentiable once but not twice?
Next, a polynomial.
It is differentiable infinite times. Infinite times. Constant, what is the derivative? 0. Derivative of 0 is 0. Derivative of 0 is 0. I am saying it is differentiable once but not differentiable twice. Differentiable once but not differentiable twice. We can define so many functions in this. One of the example is this. X mod of x. X mod of x. And when you define this function exactly, this becomes x square when x is greater than 0 and minus x square when. So what is the graph of this function? On the right hand side it's a parabola, a half parabola. On the left hand side it's a parabola. This is exactly the point where it is differentiable once. It is not differentiable twice. What is the problem? What is the derivative of this one? Derivative of x square? 2x. Derivative of minus x square? Minus 2x. What is the value of this one at 0? 0. What is the value of this one at 0? Both values are same at 0. So this function is differentiable at 0. What is the second derivative? What is the value at 0? 2. What is the value at 0? Not differentiable twice. So this belongs to C1, but this does not belong to C1. Similarly, you can say, okay, let us take this function. X square times mod of x. This is differentiable once, differentiable twice, not differentiable thrice. So you can construct the functions by just multiplying with mod of x. You can construct so many functions in this way. But this is not the case with complex valued functions. Complex valued functions are some sort of special functions. If the function is analytic, means differentiable, then it is differentiable infinite times. There's no any problem with this. And we'll be discussing why when we are coming to power series and Taylor and Laurent representation of the complex valued functions. Okay, so we are coming to discuss what do you mean by analyticity later on, but what we are going to discuss now is what we call the differentiability. So one thing is that if a complex valued function is differentiable, it means it satisfies CR equations. And what are CR equations? We can write our complex valued functions is u plus iv, where u is the real part and v is the imaginary part. And what are CR equations? Cauchy-Riemann equations. So let me write this. Cauchy-Riemann equations. So the partial of u with respect to x is same as partial of v with respect to y, and partial of u with respect to y is same as negative of partial v with respect to x. So if a function is differentiable, it means CR equations are satisfied. If CR equations are satisfied, will the function be differentiable or not? I've written implies, so there is no any converse. So we have to be careful about that. If it is differentiable, means CR equation will be satisfied. If CR equations are satisfied, then it does not guarantee that the function is going to be differentiable. And but one thing else, we can take the contrapositive of this. If CR equations are not satisfied, it will not be differentiable. If CR equations are not satisfied, it will not be differentiable. Okay, so this is what we call the contrapositive of this one. Okay, one or two last things let us discuss. You have this function, what we call a linear function in C. We know very well it is continuous and it is differentiable. It means it will always satisfy Cauchy-Riemann equations. And we can simply check that whether Cauchy-Riemann equations are satisfied or not. What is u? X. What is v? Y. What is the value of partial u by partial x in this one? 1. And partial v by partial y? 1. So the first equation. Partial u by partial y is 0. Partial v by partial x is 0. So satisfied. So if this is differentiable, it means CR equations will be automatically satisfied. What do you mean by this one? See conjugate. I told you, I think we can write this into both forms. No problem. X minus iv. What is partial u by partial x? 1. Partial v by partial y. So the function which is simply the complex conjugate of z does not satisfy CR equations, it means it is not differentiable. Can you see what is happening in this way? So one small tip is there. If you want to see that if a complex valued function is differentiable or not, you should check one thing, that it should be free of z conjugate. It means your complex valued function should not include anything like z conjugate. If there is any term like z conjugate, then your function is not differentiable. And there are some books, they rewrite these Cauchy-Riemann equations into one equation, and that equation is your complex valued function when you differentiate it with respect to z conjugate, it should be equal to 0. It should be equal to 0. Then Cauchy-Riemann conditions are satisfied. It means, what is the derivative of this one with respect to z conjugate? There is no z conjugate, so what is the derivative? 0. What is the derivative of this one with respect to z conjugate? 1. So this is not equal to 0, and CR equations are not satisfied. So the other form for CR equations is this, which is very short. It is very short, and we can check this thing easily. So if I ask you whether this is differentiable or not, C times Z conjugate, so there is a term like Z conjugate, so it is not differentiable. You are not supposed to check anything. You can directly say that okay, whether it is differentiable or not. So this is something very good that we can see easily, that whether it involves Z conjugate or it does not involve Z conjugate. Okay, what about this? It does not involve the conjugate, so it is differentiable. And so on. So we can see that whether the functions are differentiable or not. So there is another condition. Sometimes it is named as Cauchy-Riemann theorem. It is the converse of this one. Now we know very well differentiability implies CR equations, but CR equations do not imply differentiability. But if you say that CR equations are satisfied plus there is another condition which is satisfied, CR plus some additional condition, then it implies differentiability. CR equations do not imply differentiability, but if you include another extra condition with CR equations, then it guarantees to be differentiability. And this is sometimes called Borsa condition or Cauchy-Borsa theorem. I don't know exactly the name, but sometimes in some books it is mentioned like this. I will tell you exactly what does it mean. But what is that extra condition? That extra condition is U, V, and its first partials are continuous. So these U, V, and all its partials means this partial, this partial, this partial, and this partial. If these are continuous and CR equations are satisfied, then you can say that okay, the function is differentiable. So only CR equations do not imply differentiability, but CR equations plus this implies differentiability. So this is very strong condition, I think. Okay, so the next thing that we want to do, what do we mean by analytic functions and then the complex integration? Okay, any question?